My name is Hovhannes Margaryan, and my presentation topic today is classical texture synthesis and beyond. A brief outline of my presentation is the following. We'll begin with an introduction to texture synthesis, where I will give a definition of texture and the problem formulation and motivation. Next, I will start with classical texture synthesis and talk about two of the most fundamental texture synthesis algorithms. First, image quilting for texture synthesis and transfer by Adversarial et al., whose main contribution is the quilting algorithm for patch blending. And second, texture optimization by Quilting et al., where they define a Markov random field-based similarity metric and base their solution on an optimization problem of an energy function. Next, I will segue to neural texture synthesis and begin the discussion with one of the first works in the field, texture synthesis using CNNs by Yerevan et al., where they use the feature space of a pre-trained network in order to model a texture. And finally, I will talk about a more recent method, non-stationary texture synthesis by Zhou et al., where they use generative adversarial networks to learn to generate output textures that are 2 times larger than the input. Finally, I will provide a comparison among these 4 algorithms and visual results. And at the end, I will briefly conclude my talk. So let's begin with texture definition. A lot of the times, it's very hard to give a strict definition of texture. And depending on the field, such as computer science, mathematics, or psychophysics, the definition and interpretation of the word changes. In general, any surface structure can be treated as texture, but a more general and more formal way of defining texture is its structural interpretation. So texture is a spatial variation in diverse layers of pixels, demonstrating reiterating patterns combined with varied randomness in quantity. There are essentially 4 types of textures. Regular textures that imitate a regular pattern, irregular textures that are slightly more varied than regular textures, stochastic textures that look like noise but with very high variance, and non-stationary textures that contain large-scale inhomogeneous structures. The idea of texture synthesis is the following. We are given an input texture, and the goal of the synthesis algorithm is to generate an expanded version of the input that is perceptually similar to the given input. Texture synthesis is a research area in computer vision and computer graphics and image processing, and it has many applications in different areas, such as image editing and game development. In addition to that, ideas and concepts from texture synthesis can be further applied to different other research areas, such as style transfer, imaging painting, or image out painting. The evaluation method, in the case of texture synthesis algorithms, is mostly human observation or human inspection, because most of the well-known scores do not convey sufficient amount of information to assess the visual quality of the output texture. So let's begin with image quilting. Image quilting by Adversarial et al. Is a non-parametric texture synthesis algorithm that generates an output texture given an input texture. So let's formally assume that we are given an input texture I of size m by n, and the goal is to synthesize an output texture S. In addition, let's also assume that we are given a set of input patches where each patch is of size w. Now, the goal of the very naive and basic approach to texture synthesis is tiling. That is, we begin the synthesis procedure by first sampling a random patch from the given input patches, and at each step we sample another random patch from the given set of input patches and blend it over the output texture S, and we do this procedure until the whole texture S, output texture S, is synthesized. For some types of textures, this may already provide pretty adequate results, but if we take a look at an example, we can notice that at the edge of the 2 patches, a clearly visible seam is noticeable. So we want to provide an improvement over this procedure. So we define an overlap size O and search the patch of the given input patches for the most similar patch to the given patch over the overlap region. This clearly provides an improvement over the very naive approach because the two patches, Pij and Pi prime J prime, are similar over the overlap region. However, in this case too, we still have a noticeable seam at the boundary of the two patches. The final improvement that is suggested by the authors is the following. After finding the two similar patches, we also compute a minimum cost path in the overlap region and use it as a boundary during the blending procedure. If we now take a look at an example, the clearly visible seam from the middle figure has disappeared at the bottom. Now let's take a look at the whole procedure of the algorithm. So we are given an input texture I. So first we choose the patch size and the overlap size. Then we randomly select a patch from the set of input patches in order to start the synthesis procedure. Then at each step, we search the set of input patches to the most similar patch to the given patch over the overlap region using some tolerance parameter epsilon. Epsilon is essential to introduce some randomness in the output texture, but more information will be provided later regarding the epsilon parameter. Finally, we compute a minimum cost path in the overlap region and use it during the blending. We continue this synthesis procedure in the raster scan order or diagonally as it is visually represented on the slides. Now I'd like to go through each portion of the algorithm. So let's start with patch selection. So the goal of the patch selection is the following. We are given some patch, and the goal is to find the distance between the patch and the given input, every patch of the given input texture. For that purpose, we define a matrix D where each element is the MSE between the given patch and every patch of the given input texture. Then we find the minimum distance from the computed matrix D and uniformly select a patch from the set of input patches that has smaller distance than the expression that is provided on the slides. For patch selection, we essentially have two options. We can either use tree-based nearest neighbor search algorithms, such as KD trees or ball trees, or we can apply a convolution-based MSE calculation, which further can be accelerated using FFT. So formally, let's assume that we are given a patch PS, and we need to calculate the most similar patch from the input texture I. If we write the MSE between the given image and the given patch in an extended form, there is a component wherein we need to compute the MSE, the convolution of the given input image using the given patch as a kernel. And at this point, if we further want to accelerate this process using FFTs, we can utilize the convolution theorem, which basically states that the convolution operation in the position space is equivalent to direct multiplication in the frequency space. So we can use Fourier transforms to transform the given input image and the patch to the Fourier space and apply direct multiplication in the frequency space and use back transform in order to get the result of the convolution. This procedure requires only a couple of computations for the computation of the Fourier transforms, but and is therefore much cheaper than the naive approach. Now let's see how a minimum boundary cut can be computed. Let's formally define a path gamma of size of length L as an ordered set of 8 connected pixels. And let's assume that we are given two patches that are P1 and P2 that are similar over the overlap region. So first we compute Eij, which is the square distance between the two patches in the overlap region at position ij. Then we formulate the problem of finding a minimum boundary cut as an optimization problem where we need to minimize the sum of E gamma k's, where gamma k belongs to the path. At this point, let's also note that the optimization problem that is presented on the slides satisfies the principle of optimality, which implies that if we have an optimal path that goes from the bottom to the top, and if we choose a random point on that path, the path that goes from the bottom to that point is also an optimal point that goes from the bottom to that point. So we basically, this allows us to solve the optimization problem using a dynamic programming where we need to compute the cumulative minimum error boundary cut using the formula that is presented on the slide. It is basically a sum of EIJs and the minimum of the 3 points below IJ. At this point, I would like to take a look at the influence of each parameters of the algorithm. So we have 3 parameters: the patch size, the overlap size, and the tolerance. So let's fix 2 of them and take a look at the influence of the of an individual parameter. So the patch size controls the amount of information that is propagated from the input texture to the output texture. If the patch size is small, then there are more patches in the patch selection process, and therefore more randomness is introduced in the output texture. While at the same time, if the patch size is large, then large-scale verbatim copy zones are introduced in the output texture, as it is represented in the case when a patch size is equal 125. And next, let's segue to overlap size. If the overlap size is small, then the risks of in creating large-scale verbatim copy zones in the output texture decreases, while if we increase the overlap size, we can guarantee that there is a seamless transition between the 2 similar patches. But if the overlap size is too large, then there is a risk of garbage scoring, as it can be seen in the rightmost example when the overlap size is equal to 0.75. Finally, the tolerance parameter controls the amount of variation and randomness that is introduced in the output texture. If epsilon is small, then there is a risk of creating large-scale copies in the output texture, while if we increase the tolerance parameter, there are more patches in the patch selection process, so the output texture is more random and it contains more variance. The next classical texture synthesis algorithm on the menu today is texture optimization. Texture optimization by Quilting et al. Is again non-parametric texture synthesis algorithm, and they base their solution on the following 2 assumptions. Let's first of all assume that a texture follows the Markov random field property, which in the case of textures comprises locality and stationarity. Locality implies that the pixel intensity value of a given pixel is only dependent on pixel intensity values in its neighborhood, while the stationarity assumption refers to that the dependence is independent on the position of the given pixel. Second, let's also assume that if all neighborhoods of the output texture S are equal to sum of the neighborhoods in the input texture, then the output texture S is considered as similar to the given input texture. Next, we formulate the texture synthesis procedure as an optimization of an energy function. Let's formally assume that we are given a patch SP around pixel P of size W, and we are also given a patch IP from the input patch that is the most similar patch to the given patch SP. The texture energy over the whole output texture S is defined as a sum of L2 norms between SP and IP, and for all neighborhoods in the output texture. In practice, we only choose to work with a subset S star because it is computationally less expensive, and in general, it is redundant to have the all neighborhoods in the output texture. Let's see how the algorithm performs. So we are given an input texture I and some initialization of the output texture S, and we iterate the following 2 procedures until convergence. For each SP, we find the closest input neighborhood IP, and next we update the output texture S by optimizing the energy function that was presented in the previous slide. As I mentioned, we need some initialization of the output texture S to begin the synthesis procedure. If we are not provided with an initialization, we randomly assign input patches to IP. And the last question that remains is when to stop the optimization procedure. And the authors in this case suggest halting the optimization procedure when IP stops changing. The optimization problem that was presented in the previous slide can be loosely treated as expectation maximization. In the energy function, we treat the output texture as variables, while IPs as parameters. Then, in the each step, we minimize the texture energy function with respect to S. And since the texture energy function is quadratic, we end up solving a system of linear equations. An interesting case is when two patches in the output texture S overlap, namely SP and SQ. Then in the overlap region, the pixel intensity values are drawn to two different input patches, IP and IQ. And therefore, from this perspective, the goal of the E step is to assign the average of the corresponding pixel intensity values from the input texture to the overlap region in the output texture. In the M step, we minimize the texture energy with respect to the IPs, hence the parameters. And this corresponds to nearest neighbor search that was also introduced in the image quilting algorithm. And authors implement nearest neighbor search using KD trees. In addition to that, the authors suggest running the texture optimization algorithm in a multi-resolution and multi-level synthesis. And the motivation of this approach are the following. So the output texture result and the convergence of the algorithm is dependent on the initialization of the output texture. In addition, the patch size, if the patch size is small, then there is more variation in the output texture, but at the same time, we may not capture large-scale structures. And if the patch size is large, then large-scale verbatim copy zones may be introduced in the output texture. And finally, the right choice of the patch size is highly dependent on the resolution of the input texture. So the idea of applying multi-level and multi-resolution synthesis is the following. We start at a very low resolution and use different patch sizes at each resolution from largest to smallest. Large patch sizes help us capture large-scale structures, while small patch sizes apply a further refinement step over the output texture. And at the next resolution level, we use the current resolution's output and upsample it and use it as an initialization to the next resolution level. This helps us avoid getting stuck at bad local optimum. Now let's see the influence of resolution levels on the output texture. As it can be noticed, as we increase the number of resolutions, the visual quality of the output texture increases and the risks of garbage growing decrease, as it was the case when the number of resolutions is equal to 1. Finally, let's segue to neural texture synthesis and begin our discussion with texture synthesis using CNNs by Gades et al. This approach is a parametric texture synthesis algorithm, and therefore we need to explicitly define a texture model. The authors assume that textures are stationary, which means they are homogeneous and they don't contain large-scale structures. Formally, let's assume that we are given an input texture I, and our goal is to synthesize an output texture I hat. The texture model is computed in the feature space of a pre-trained VGG, the architecture of which is shown on the right. And the goal is to start from a noise and optimize the output texture to obtain a output texture that has a similar texture model as the given input texture. So in order to define the texture model or the summary statistic, let's also assume that we are given FL, which is a matrix that contains the feature maps from level L. Then formally the summary statistics is a set of gram matrices where each gram matrix is an inner product between the feature maps from layer L. Then, in order to formulate the problem as an optimization problem, let's also assume that we compute EL, which is the sum of square differences between the gram matrices from level L between input and output textures. And the loss function is formally then defined as a weighted sum of ELs. Now let's see how the whole algorithm works. We are given an input texture I and some initialization of the output texture I hat. We begin by first computing the summary statistics of the given input texture I. Then our goal is to optimize the loss function that was presented in the previous slide in order to obtain an output texture I hat that has similar summary statistic as the given input texture. Let's also note at this point that the gram matrices are calculated using only convolutional or pooling layers, and therefore the output can have arbitrary size. In this case too, we begin the initialization of the output texture from a white noise, and the authors optimize the loss function using LBFGS. Let's also take a look at the influence of layers that we use to calculate the gram matrices. The name of the layer that is shown on the slides is the topmost layers, which means that all the preceding layers have been used in the calculation of the gram matrices. So it can be noticed that in the first layers, only the general structure of the texture have been captured, while if we if we go deeper in the network, then the visual quality of the output texture improves and more details are added to the output texture. The final texture synthesis algorithm that we will cover today is non-stationary texture synthesis by Zhou et al. This particular algorithm is designed to handle non-stationary textures which contain large-scale inhomogeneous structures with spatial variation in different attributes such as color, local scale, or orientation. In this approach, we are going to use generative adversarial networks to learn to generate output patches that are 2 times larger than the given input patch. Let's formally assume that we are given an input exemplar texture and a patch from the given input texture, and the goal of the generator network is to generate an output texture that is 2 times larger than the given input texture. So S, in this case, the output texture is S of size 2 times W. And the goal of the discriminator network is to classify whether the given its input comes from the given input exemplar texture or is generated by the generator network. Let's also note that in this case we deal with self-supervised learning because the ground truth I is directly taken from the given input exemplar texture. The loss function comprises of the adversarial loss, the L1 loss, and the style loss. The adversarial loss in this case is the main driving force, while the L1 and style losses are added to the total loss in order to stabilize the training, reduce the artifacts, and improve the visual quality of the output texture. In this approach, we need to train a separate generator for each given input exemplar texture. Now let's take a look at the very general architecture of the generator network and the training procedure. The generator network is fully convolutional, which implies that it can take inputs of arbitrary sizes. Particularly, the given input exemplar texture can be given as an input to the generator once it has been trained in order to obtain an output texture that is 2 times larger than the given input exemplar texture. The generator network comprises of convolutional layers and residual blocks in 6 in number. So the residual blocks are added to the architecture of the network, so we can go deeper in the network to increase the receptive field of the network, and at the same time try to avoid any potential problems we can have during the training procedure. The receptive field at the end of the last residual block is 106, which is very close to the patch size W that the authors used during the training procedure. The training works as follows. We randomly, at each iteration, we randomly select a patch I of size 2 times W from the given input exemplar texture, and this I is going to serve as a ground truth. Next, we randomly select a patch W from I and give it as an input to the generator. The training procedure is optimized using the Adam optimizer. Let's now see the influence of each loss term on the output textures. So we begin with the adversarial loss, and we can notice that only the general structure has been captured, while as we add the L1 and the style losses, the visual quality of the output texture improves and more color and details are added to the output texture. Let's also see the influence of the patch size in this case. So the general idea here is that the patch size should be large enough to capture large-scale structures and propagate it from the input texture to the output texture. This is especially essential when we deal with non-stationary textures. And the patch size should be small enough so as we can get sufficient amount of distinct patches of size 2 times W to serve as ground truth. Let's now go over a comparison among these 4 algorithms. So the primary advantage of image quilting, texture optimization, and texture synthesis using CNNs is controllability. In the case of image quilting, controllability refers to the idea that we can modify the parameters so as to handle most types of textures except to non-stationary textures, which cannot be handled in 3 of the algorithms that we saw today. In the case of texture optimization and texture synthesis using CNNs, the controllability refers to the idea that we can modify the energy or loss functions so as to handle specific texture cases or improve the visual quality of the output texture. Non-stationary texture synthesis can handle all 4 types of textures. And in addition to that, non-stationary texture synthesis can generate very large textures if the output texture is given back as an input to the generator. The speed is only an advantage in the case of image quilting, while in the case of non-stationary texture synthesis, we have very fast inference speed. The training speed is quite slow. And another disadvantage of non-stationary texture synthesis is that it requires training a separate generator network for each given input exemplar texture. Let's go through some results, and in this case we can notice that in the case of regular textures, the only algorithm that fails is texture synthesis using CNNs. In the case of irregular and stochastic textures, all 4 algorithms provide satisfactory results for human observation. And in the case of a non-stationary textures, we can notice that the only algorithm that has been able to capture the non-stationarity and large-scale structure of the wood is non-stationary texture synthesis, while the rest of the algorithms have failed. Particularly in the case of texture synthesis using CNNs, only the style has been captured, while the large-scale inhomogeneous structure of the wood hasn't been captured by the algorithm. So let's also conclude today's presentation. So today I went over 4 texture synthesis algorithms, classical and neural. Image quilting is a fast and controllable algorithm that handles regular, irregular, and stochastic textures. Texture optimization is a slow but controllable algorithm, and it handles all the same types of textures as image quilting. Texture synthesis using CNNs is a slow but controllable algorithm, and it handles only irregular and stochastic textures. Non-stationary texture synthesis provides very fast inference, and it handles all 4 types of textures, that is regular, irregular, stochastic, and non-stationary textures. Here are some references if any of you is interested in further research. Thank you for your attention.